Okay, so I hope you can see my screen. So you need to start writing P in the chat window in the first part of the lecture, and we will continue with our discussion of discrete time Fourier series and then DFT, discrete Fourier transform. So I'm actually skipping some parts of the lecture, some parts of these slides. So because they're very similar to what we had before. The only difference you see will be this capital omega, and by now it should be very clear that this is the discrete time frequency, right? Discrete time frequency. And by frequency, we mean angular frequency to make sure that it's not the, it should not be confused with cyclic frequency. And apart from this symbol, you see, you typically have those regions, pass band. So it is the region of frequencies for which if you have an LTI system in mind, right? So that LTI system, you imagine a time domain, discrete time signal, right? And the output will also be a discrete time signal. So what we mean by such a plot, such a frequency response. So remember, frequency response is the name we give to how the system actually behaves with such signals. So to be specific, frequency response is the name given to the transfer function when you evaluate it at the omega axis. So you usually when you have, for example, if h is the transfer function, it will in continuous time it will take s, the Laplace variable, and in discrete time it will take the z. Yeah, I mean we are yet to discover z transform, um, but the counterpart of s in discrete time is z. So if we now replace s with j omega, yeah, then we are restricting ourselves to the omega axis, and that is what we call the frequency response in continuous time systems. So we will have a similar distinction between transfer function and frequency response. So maybe we should wait for the Z transform before I get to this. Yeah. So why we are calling it frequency response, we get to this later. But the thing which you can understand is that the region of frequency axis, which has a non-zero frequency response, that will be passed, and that's why we call it pass band. And the regions um, which are actually blocked by the system, they will have a zero response, right? Zero response, zero frequency response. And yeah, these cutoff frequencies and so on and so forth. So maybe I get to these things later. So now we need to actually get back to a scheme. So I'm not revising everything in this course, but let's focus only on the frequency domain. So what we have done so far in the frequency domain in this course, right? So we first started with periodic signals in continuous time, right? Periodic signals. And it turns out that the best tools to understand frequency contents of periodic signal is the continuous time Fourier series, right? And then later on, we expanded that idea to aperiodic signals. And in aperiodic signals, we had two actually cases. One was when the energy of the signal, or I would say signal energy, when it was finite. Yeah. And the other cases when the signal energy was not bounded. Signal energy unbounded. Yeah, I can you can recall things like, for example, signal like that or like that. They are bounded in energy, but the step signal or the periodic signals, period. I mean, they don't have finite energy. So we had for these signals we developed continuous time Fourier transform, the traditional one, right? The traditional continuous time Fourier transform, and that integral didn't converge for such signals, so we had to generalized. So then we developed generalized continuous time Fourier transform, and I mean when we simply say CTFT, we mean both traditional and generalized, right? And then we moved on to Laplace transform. So Laplace transform was actually built on top of CTFT, and we introduced the real axis. Yeah, so let's explain what you see on the omega axis. Everything you compute on the omega axis is just a repetition of CTFT, um, the classical one. And signals for which we had conversion issues, for that we introduced this real axis, sigma axis, and that allowed us to control the region of convergence, and that's why you have those ROCs. So one thing is now very clear that um, Fourier transforms cannot be used for stability analysis, right? Because stability is something related to convergence, and without this, yeah, real axis, you can't have convergence. So Laplace transform is the only serious tool for stability analysis as of now. I mean, there are shortcuts, but yeah, you don't know those shortcuts. Then we moved on to discrete time signals, and in discrete time signals, we started right away with periodic sequences. So when we say sequences, we mean discrete time signals. And the tool we discovered uh, was discrete time Fourier series. Um, so not only the signal is periodic, the Fourier coefficients are also periodic. So if you have a signal x of n and you convert it to you transform it to, let's say, ak for the discrete time Fourier series, it turns out that not only this is periodic, but these were also periodic, right? And later on, what we did that we introduced DFT, and DFT was actually restricting uh, both the time domain signal and the coefficients to just one period. So if you restrict everything to one period in both the frequency domain and in the time domain, right? I'll just call it N and K, N for the time domain and K for the frequency domain, and you restrict everything to just one period, right? One period, and then you leave everything undefined outside it. Um, and then you get what you call the DFT. Yeah? So apart from restricting to one period, there was also another change, if you can recall, and it was this 1 over n factor, right? So this 1 over n and dtfs was with the transform, right? So when you are computing transform, you have this 1 over n and then summation and things like that. But in this discrete Fourier series, this 1 over n was brought to this side. Yeah. So we are computing the time domain signal from the frequency domain signal. Then you had this 1 over n, right? So now, I mean, that should be a quick summary of what we did so far. Um, if there is any question, I can take one or two questions, because now what I'm doing now is the next topic, and we will now leave periodic signals and we will switch to discrete time aperiodic signals, right? So, and that brings us to discrete time Fourier transform. So just like you had continuous time Fourier transform, and we needed continuous time transform for aperiodic signals, right? So similarly, for aperiodic discrete time signals, we need this tool, discrete time Fourier transform. So this is just a recap. I mean, although it's for discrete time, but it will remind you many of the steps we needed in continuous time. So the discrete time Fourier series we discovered last time. It is an extremely useful representation, but only for periodic sequences, right? We sometimes need to deal with sequences that are not periodic. So a more general tool replacing Fourier series is needed, and that is what is called the discrete time Fourier transform. And it can be used for both periodic and aperiodic sequences because we will sooner or later introduce generalized as well. So when you introduce generalized Fourier transform discrete time, that can also deal with periodic sequences. So to summarize these points, you can think of discrete time Fourier transform as a limiting case of Fourier series. Yeah, when you allow the period n to approach infinity. So yeah, I'm skipping all these derivations. Okay, I'll switch straight to the. I mean, the steps are very similar. You pretend that you have a periodic signals, and the period is, let's call it n instead of t. Remember, we use t for continuous time period. So you start with an n periodic sequence and develop the Fourier series because it's periodic, and then you apply this limiting process n approaching infinity, just like we had t approaching infinity. So I think you can recall many of those steps. Um, you have summation instead of integration, and if I actually fast forward, what you get at the end is the classical Fourier transform. I was calling it traditional, but some authors also call it classical. Yeah, so it is not the generalized, um, and because it can have issues with convergence, right? You have convergence issues because you will get a summation like that. So maybe in the previous slide, I can now introduce the classical um, discrete time Fourier transform, which is this thing, right? Forget about everything else, just focus on this thing. You start with a discrete time signal, right? L is a dummy variable, so you can replace L with anything. That's not important. So you start with a discrete time signal, you multiply it with these complex sinusoids. Remember, I'm using complex sinusoid, not complex exponentials. Why? Because the real part is zero in the exponent. So um, yeah, and then when you sum it over all possible values, you get this discrete time Fourier transform. And the connection to the continuous, sorry, to the discrete time signal is through the inverse transform, and the inverse transform is in the form of an integral. Now you must be wondering, why do we have this integral when we are dealing when we are dealing with discrete time sequences? So this makes sense, right? This thing makes sense. I start with a discrete time signal and I have to sum it to get the discrete time Fourier transform. So why do I need integral to get a discrete time signal? Any idea? Hmm? Why not sum on both in both cases? So that can be answered by thinking about this capital omega. What can you say about this capital omega? What is the nature of this? Of course, we call it the discrete time frequency, right? But that is only a name. What is the type? Is it an integer? Is it a real number? Hmm?
Interior.
Omega is an integer. How did we define it? Remember, it was 2 pi divided by n, right? Just like this small omega was defined as 2 pi divided by t, right? So when you have 2 pi in it, it cannot be an integer, right? So omega is actually a real number. It's a real quantity. We call it discrete time frequency not because it is an integer, but because it is the frequency of a discrete time signal. That is what you need to keep in mind, right? And this 2 pi by n was actually not omega, it was omega naught, I think. Yes, it was omega naught, the fundamental one. So when you have a function which acts on real numbers, you have to integrate it. And one more thing, why do you have this 2 pi? What does this indicate? What does this actually mean to have a 2 pi as the lower? Uh, I wouldn't call it a limit. I mean, a better notation which I would recommend is this thing, just like this. Yeah, I would recommend this angle brackets, because otherwise somebody can think of this as a typing mistake, or you have a lower limit but you forgot to write the upper limit, right? That's what many people think of it. So the best way is to write these angle brackets. So angle bracket will ensure that it's an integral over one period, right? So here the period is 2 pi because this discrete time Fourier transform, which we just discovered, it turns out to be a periodic function. And the reason for that is the definition. If you look at the definition, right, you have a discrete time signal, but you multiply it with this complex sinusoid. That complex sinusoid is periodic, right? So summing a periodic signal will give you another periodic signal. So we can now have the final definition, okay? And before the final definition, just remember now that the classical definition, I'm just writing it down, okay, this one. Instead of writing it down, I'll just highlight it. This is the classical definition of x of omega, right? I'd call this x of omega. And see what is going on. You start with a discrete time signal, right? And then you multiply it with a complex sinusoid, and then you sum it over all possible values of n, and then you get x of omega. Because n is in the index, so it will disappear in this summation, and then you have this. Now, this summation is a summation over all integers, so it may or may not converge. So if it will only converge, yeah, if the signal has finite energy, right? If the signal has finite energy. If it does not have finite energy, it will not converge. And there are many examples like that: constant sequences, yeah, periodic sequences, unit step. It's very similar to what we had in continuous time. And then for these signals, you have to introduce the extended definition, and that is what we call the generalized Fourier transform, and that will introduce, yeah, I mean the delta, for example, the Dirac delta. So now this is the final uh, definition. You start with a signal small x, continuous time. You apply this Fourier um, transform, and although this is now, I mean, what I have been telling you over and over. Although we are using the same symbol F, how do we know if this symbol F represents CTFT or DTFT? So the symbol F cannot tell that, okay? Because it depends on the type of object you are providing it. So if you apply F to a continuous time signal, then it will become CTFT. But if you apply it to a discrete time signal, and we know that in this chapter, small x represents a discrete time signal, although we are calling it small x, but we know the type, right? We know the type, so the change, the symbol, this calligraphic F also gets a new meaning, right? So this is now a continuous time, sorry, a discrete time Fourier transform, and you need to make sure that you put a bracket there, right? For your own understanding. So you apply it to the signal, and then you evaluate it at this omega, right? And if you forget to write it down, just remember that the transform is a higher order operator, so it has to act before you can evaluate it at omega. And because we are calling this capital X most of the time, so you can write it in this way, and this is now your final definition. And this definition, if it converges, you have the classical transform, and if it doesn't converge, then you will have this generalized transform. And the inverse transform, when you go back from the discrete time Fourier transform, you apply the inverse, and maybe you can put a bracket, and then you evaluate it at n discrete time, right? And that, now you need to understand this integral. You need an integral because omega is a real variable. That is the first thing you need to notice. And you need to make sure that these two are conjugates. So if that is with a minus sign, this has to be with a plus sign. And the other thing is that the integration has to be only over a single period. I'm now putting these angle brackets. The reason for that is that x itself is a periodic signal, right? X is periodic and this is also periodic, so multiplying two periodic signals, you get another periodic signal. And this, yeah, 1 over 2 pi is just like you had 1 over t, right? So this is now our final DT-FT pair, right? So this pair is now a Fourier transform pair. So we need a few examples, okay, before I get to, I mean, he's now introducing convergence, and when this sum does not converge, if it converges, then you call it absolutely summable, and this you can show that it converges uniformly. Um, so, but if the energy, remember I told you something related to finite energy, right? So when I said finite energy, I had this thing in mind. I did not have this in mind, right? This is very rare. We don't have this for most signals, but we just need to know the complete definition. So there are two ways in which it can converge. This sum can converge in this sense. It will be called absolutely summable. This sum can converge in this sense, and this we will be calling it square summable. So, and this is why you have to use the finite energy classification. Um, the advantage of absolutely summable is that you will have uniform convergence, right? And the advantage of this finite energy is that you will have this MSE sense. Remember, MSE is mean squared error. Mean squared error. So the mean squared error is finite. So let's get to a few examples because the slides don't have examples. So let's have a few examples from the textbook just to have some sense. This is the transform pair in the textbook, right? Forward transform and the inverse transform. So let's pick this example 11.2. So you are given a rectangular pulse. And we pick this rectangular pulse because we have been using this in continuous time as well. So you'll be able to relate it. So if you define your signal in this way, you have discrete time unit step at A and discrete time unit step at B, and you subtract one unit step from another unit step, and you need to make sure that A is less than B because you want this discrete, I mean, it will look like this, right? It will look like discrete time signal starting at A, right? And then you have another discrete time signal. Let's say it starts at B. So let me use different color, right? So the discrete time signal starting at B will be like that. And now subtract this one from this one. So what do you get? How will you plot it? Hmm? Where will be the first? All these are zeros, right? So where will be the first non-zero? Can you tell me? Hmm? Any idea? This signal, I mean, I have to diffuse different colors, right? This signal is plotted here. It all goes all the way to infinity starting from A. And this one starts from B, goes all the way to infinity. And now we are subtracting the second one from the first one. So because these repeat and they are identical, so they will just disappear because you are subtracting them from one another. And you are only left with this. It has to go from A to B minus 1, right? From A to B minus 1. Because B and onwards, they get subtracted. And that's why you have this definition, yeah? X of n is now 1 when n belongs to this interval. And this interval starts at A, remember? And it ends before B. That's why you have this round bracket, right? So the values are actually A, A plus 1, A plus 2, all the way to B minus 1, right? And 0 otherwise. So now how do we compute the discrete time Fourier transform? Discrete time Fourier. So what is the definition? This is the definition, right? You start with the signal, you multiply it with the complex sinusoid, the conjugate, yeah, the minus sign. Remember the minus sign. And we need to use the capital omega because the discrete time frequency and sum it over all possible values. So let's work it out. Instead of showing it here, I need you to work it out yourself. So we know the first thing we need to do is to check the limits. The limits will generally go from minus infinity to plus infinity, but here we know that the actual limits are only determined by this. It's 0 otherwise. So the first thing we need to do is that n goes from A to, what is the upper limit?
P minus 1.
Yeah, B minus 1. So x of n exponential minus j omega n. And now we need to deal with this thing. So now you need to understand something. This before attacking this, you should just think about what is the kind of summation you had seen before. Whenever you have summation from one limit to another, the simplest form to deal with is, if you remember, it's geometric series. You can remember that geometric series, right? So
Yes,
let's
sir.
let's hold this and go to another page and see what can we recall from the geometric series. So let's say I have a series, and let's say I write n equals a, and let's say I write b minus 1 here. I can write b as well, but because I know that is b minus 1, so it's better to have it in this way. And here I'll use some number. Let's use a complex number z, right? Z can be any complex number, and this will be n. So can you say something about this sum? What can you recall from? It looks like a geometric series, right? What can you recall from your um, courses of dealing with sequences and series? I think it was something like we see this as a common ratio. So in the denominator, you will have 1 minus z or z minus 1, right? And there it was 1 minus. You had the first term here. What was the first term? Z to 8th, yeah? And it was 1 minus z to, what do we have here? Who can recall that? Hmm?
So it was something like A into R n
Yeah, so
minus
R, instead of R, we have Z, right?
1.
No, you had this. So what you had is this, okay? A plus AR, right?
Yes.
Plus AR squared. And what was the last term?
ARn minus 1.
Okay. And now, can you now recall the formula? 1 minus R, A. I forgot this part. What was this?
R power n.
So it was n, okay? And this n required this to be n minus 1, right? Now, why did I write z to n? Z to eighth, yeah? So here a was the first term. Here z to a is the first term. So this matches, right? First term, first term. R is the common ratio, Z is the common ratio. One, so we only need to fill this. So can you now tell me what will that be? Remember, n is the number of terms, right? So that is the importance of giving names. What is the name you can give to this n? Number of terms. You have n terms here. So what is the number of terms in this sum? Tell me. Is it b minus a? Right?
Yes.
Why not b minus 1 minus a? Because that one is also included, right? So I told you whenever you are dealing with discrete quantities, when you have two limits, right? This one and this one. So you subtract the lower one from the upper limit, but because the one of the endpoints is included, so you add that as well. So it will be a plus b minus 1 minus a and then plus 1, right? So that turns out to be, no, sorry, this a is not included, yeah? So b minus 1 minus a and then plus 1. Yeah, it's b minus a, right? It's b minus a. Let's remove all the unnecessary parts. I can simplify this to z to the eighth power minus, what do I get when I multiply these two? Z to the bth power, yeah, a and a cancels out. And here I'll have 1 minus z, right? Can you find any problem? So let's trust that what we did so far is correct. There is still an issue, and I want you to figure it out. So let's say you can recall everything and you were helping me and we had all this nice formula, okay? So there is still an issue. What is the issue? And to help you, I'm now making these cases, okay? Can you give me the conditions um, under which this formula is allowed to write? Hmm? Write the condition here. And that condition has to be on Z. Hmm? What is the condition on Z for this computation to be valid?
R was less than 1.
No, that
No.
that that, that was for the infinite series. This is finite. So you don't have that issue, right? Actually, what you mean is this R magnitude, right? R magnitude was just less than 1. That was for infinite sum. This is not an infinite sum, so that is not an issue. There is another issue. You can see it right in front of you. Think about it.
A is not equal to B.
No, I'm
Mm.
first asking about Z. We get to A and B later on. Alright. Don't you see anything required by Z? What happens? I mean, you have a denominator, and that denominator can become 0, right?
Z can't be 1.
Yeah, so Z can't be 1. Why do you not see this? Hmm? I mean, this you have seen this so many times in this course. So now that is the first thing you need to keep in mind. Now get to A and B. What conditions do you so when Z is equal to 1, right? When Z is equal to 1, what do you get here? We get to A and B later on, okay? What happens when Z is 1? Don't apply L'Hopital rule, okay? That is stupid. You know that is stupid. So when Z is,
Undefined.
so you have to get back to this thing, right? So just apply this, right? It will be sum n from a to b minus 1, and just write 1. There is nothing wrong with it. 1 to the nth is 1. So now, can you simplify this? We are just adding how many ones you are adding? B minus a, right? We know the number of terms is b minus a, right? Now, both of these formulas are only valid when b is, now you need a condition. So now you have another condition on top of this, right? Now I have another condition, and this only makes sense when, so I will say that this formula only makes sense when a is, what is the relationship between a and b? And let me write b minus 1 here. Yeah. So what is the relationship between a and b minus 1 for this, for both of these formulas to be valid?
A should be smaller than B because then it will be a negative sum.
A should be smaller than or equal to b minus 1, right? Equal is also fine because you have just one term, right? In other words, a is smaller than b. So what happens when a is greater than b? Hmm?
Negative sum.
Negative sum. That's the whole, that's the problem, okay? So you are now confusing it with this thing, right? When you have an integral be a to b, and I don't care what is here. And if a is less than, if a is greater than b, right? Then you write it as b to a, and you write a minus sign. Yeah, that is what you have in mind, right? That doesn't work with summations. The convention for summation is that this sum, I told you to think in terms of set, okay? So you have to write in, you have to think in terms of a set of values. So when you have such a condition, you have to actually know term. So the convention is that it will be an empty sum. So it has to be 0, okay? So it has to be 0. I will say, okay, this this whole thing is true if a is less than b, and if a is greater than b, greater than or equal to b, then this will be 0. That's what you need to remember. That is the convention. The sum is by convention 0 whenever the lower limit is larger than the upper limit. There is no such thing as a negative sum, right? So let's get back to that question now. We started with this, and now you're going to tell me what should I do with this. What is x of n in this range? 1, right? So this will be 1, right? And now tell me, how can I rewrite this to use that formula? So I have to use this, n equals a b minus 1, and I need something raised to the nth power. What is that something? Right? So what I had, the z I had on that page becomes exponential minus j omega in this page. So can you now tell me those two conditions?
This exponential one we want.
So when exponential minus j omega is 1, I have b minus a, right? I'm just copying it from there, right? When it is 1, then it's just b minus 1. And when it is not 1, it will be like that, z to a minus z to b, 1 minus z. So I'm just copying it. So when this thing is not equal to 1, it will be 1 minus z. And what is z? Right? And this was, the first term is 1, right? No, is it 1? No, you have this, yeah, z to eighth minus z to bth. Okay, so exponential minus j omega raised to eighth minus exponential minus j omega raised to bth, right? And if and they're both true when a is actually less than and here is another hint for it. Maybe I told this in some other course as well. This is a set, right? Because this is a set of values. This set becomes empty when a is greater than b, right? So if a is greater than b, by convention this has to be empty, and that is why you have the sum of an empty um, set of values is zero. And you can now simplify this, right? When you simplify this, you can connect it to Euler identity, right? You have these exponential, I mean, the exponential x minus exponential minus x. Yeah, if you have j and by 2, this is cosine. And if you have a j here, it is, sorry, if this is cosine, and if you have minus and 2j here, it becomes sine. So I think I trust that you can follow that. He's now following all these horrible calculations. And at the end, you get this thing. Uh, I don't want to actually do it in all the detail. I gave you enough hints, and I don't expect you to simplify it either. I mean, if you leave it like that, it's enough, right? If you leave it like that, it's perfectly okay. I don't care whether you can simplify. But let's say that you are asked to critique what you see in the textbook, okay? So what objection will you have in this final form? You should be able to tell me that. I want you to give me that case, yeah, because this will only be allowed for some values of omega, and for others, you need a different answer. So now pay attention to this condition. What do we require here? Exponential minus j omega equals 1, and exponential minus j omega not equal to 1. How does this translate to a condition on capital omega? Can you see that? What does this condition mean in terms of omega? Omega must equal,
One.
no, 0. Exponential 0 is 1, right? This is the exponential omega minus j omega is equal to 1. So omega is 0. And this translates to omega non-zero, right? So this expression which you see in the textbook is only allowed to write when omega is non-zero. You can see it, yeah? You have 0 by 0, sine 0 by sine 0. So when omega is 0, what you are going to do? I have already told you. You need to stop thinking about this, right? All of this is nonsense. And you have to go back to the original summation, right? You have to solve it at the correct spot. This is the correct spot, right? When omega is 0, 0, this is 1, and this simply gives you b minus a. So write b minus a, right? This would be minus a. And I don't care whether you can simplify it or not, right? Now here in the example 11.3, are there any questions in the first example? Hmm? Think about it. Because the next example, so because the sum here was finite, so you can easily say that this was the classical transform, right? We didn't need any generalized transform. But the next summation is actually no, here it's also classical because you have this real constant a, right? So let's work this out, right? And then we are done. So before I get to that, let's go back to that summation and let me change the upper limit, right? How will this simplify when the upper limit is infinite? So, so if I start with n equals a and this is infinite and this is z to n. So now what can I have? Hmm? Because this is an infinite sum, so here I do need the absolute value of z to be less than 1, right? And otherwise, it's undefined, right? And this formula is much simpler if you can remember it. You have 1 minus z here, and all you need to do is to write the first term, and that is z to the 8th power. I think it was this thing. And when will it be 0? Both of these require n to be, so I can say n to be um, oh, of course, n cannot be larger than infinity, so you don't need that condition, right? That's enough. So now you have this sequence a, and you are given this extra piece of information that the absolute value of a is less than 1. So if you now apply this summation, right? This is your x of n, this is x of n, this is the exponential, and if you now apply that formula, the actual values are from 0 to infinity because u of n is only non-zero. U of n is only non-zero for non-negative values. So it's now simply a to the nth exponential minus j omega to the nth. And now I can simplify this, right? And now I need to write this as something raised to n so that that common ratio is found. And what is that something? Can you simplify it? Of course, we need that exponential minus j capital omega like before. And here we need a, right? So now this is, yeah, this is what you had for z before, right? And now you can easily say that, okay, it will be, because it's an infinite sum, so it will be 1 minus z, which is a exponential minus j omega. That is my z. And here it's the first term. The first term is a exponential minus j omega to 0. Yeah, 0 is the first index. So this is 1 simply. So 1 over 1 minus a exponential minus j. And the condition is that um, exponential a exponential minus j omega absolute value is less than 1. Now you need the importance of this thing. Yeah, exponential. So the absolute value of a is less than 1. Has been given to you, right? So that is never a problem. That is already given to you. So you should only worry about this part. So what should we do there to ensure this condition? I think we don't need to worry because this exponential minus j omega itself, what is the magnitude of this alone, regardless of the value of omega? The magnitude will always be 1, yeah, because it's on the unit circle, right? I told you this, you can think of this one as the radius, and yeah, this only rotates along this unit circle. So there is no issue of convergence arising from omega, no? And that's why that is the only condition you will see in the final result, right? It's just a simplification. and you can now follow up all the other examples. We can now move straight to properties. Okay, I typically work these few examples out so that you see the mechanics of the transform. So let's get straight to properties. The properties should be very similar. I mean, there are a few new properties, of course. So linearity, can expect it. Any transform so far has linearity. And then you have this translation, right? It looks very similar. And just make sure that you can identify this shift as something which multiplies the discrete time frequency, right? And the modulation, right? So translation is time shift, and modulation is frequency shift, because in modulation the shift is visible in the frequency domain, right? And conjugation, time reversal, and because these are discrete time signals, so you have upsampling and downsampling as well. Yeah, upsampling by a factor of n, m, and downsampling by a factor of m, right? And you can see here that in the frequency domain, you have if m is larger than 1, so you get more, and I mean, you have a compressed, right, um, uh, transform. And convolution, yeah, uh, corresponds to multiplication in the frequency domain, and multiplication corresponds to this thing. Yeah, I mean, you can think of it as periodic convolution, because x1 and x2 are periodic, right? You can, I mean, there should be, you can write this as x1, x2, and periodic convolution, right? And you see some more properties. Frequency domain differentiation. You differentiate with respect to capital omega and this with this J sign. And in time domain, it's multiplication. It's very similar to what you had in Laplace transform. Yeah, it was x of t, and this was t by ds of x. And you have differencing. Yeah, you subtract a translated version from the original, and you have this thing. And you have accumulation, right? Accumulation is that when you start from a particular value n and you add all the previous values. Yeah? So you go from n and n minus 1, n minus 2. So everything before n, you're adding it. That's what is called accumulation. So you see, it looks very similar to integration in time domain, continuous time. In continuous time, you had this integral there, right? And you had something very similar there. Um, and instead of differencing, you had differentiation in continuous time. So I think I would recommend to print this and keep looking at this a few times, and you would get a sense of how to apply, right? Yeah, the most important property is this one. You need to realize that this dtft is actually periodic, and that is why the integration is only over one period, right? So even the Parseval relationships is simple. In the frequency domain, you just have to integrate over one period, but in the time domain, right, because the signal is aperiodic, or it doesn't need to be periodic. So you just don't apply this Parseval relations to periodic signal, because this will not exist, right? This thing will not exist. And that's why you will need generalized transforms. And then you have this x even odd symmetry. Yeah, x is even, x is odd, provided they are both real, right? And you always remember that thing, that when it is odd, it is purely imaginary, and the transform is purely imaginary. So you should write this j with it. This is a typing mistake in all of these tables. Yeah, so this was the transform properties table, and this is now the table for common pairs. So maybe we can just, um, we already had worked for some of, I mean, we tried to derive this one, right? One of the examples was this. We already saw this. And you can now, maybe you can use some properties. It's imaginable that you can start with this and you use some of these properties to derive this. Can you imagine what will you need to derive this from that? What operations, what properties will you need? Hmm? So if we start one by one, what property will be needed for this minus sign? Hmm? Look there in the table. Who can tell me which property is needed? I'm forgetting about everything else. I'm just looking at this minus sign. Hmm? No idea? It's just changing the value. You don't change the time. So which property is dealing only with the value of the signal? Tell me. First one, right? They're just multiplying a signal by a constant. So that constant can be minus one and forget about the rest of it, right? So you need linearity. And what else do you need? You need time reversal, right? Time reversal, time reversal, right? And after time reversal, you have to apply translation. So three properties are needed to go from this, right? To go from 4 to 5, you need linearity followed by time reversal followed by translation, right? And I told you to remember one thing is that the main motivation for the classical transform was aperiodic signal. Now these two are periodic signals, right? So ideally you should only be using discrete time Fourier series for them, and you should not be using discrete time Fourier transform. But we have to in this chapter. So what do you see there which explains that unusual nature? Can you see something? What was the important point about trying DTFT on periodic signals? And we had this problem in continuous time as well. Who can recall that? Hmm? I told you that periodic signals and constant signals, for them, the classical transform does not converge, right? So you will have to use generalized transform, right? And what is special about generalized transforms? You see, which delta? Hmm? Can you give me the name for this?
Dirac delta.
And in this same table, we are seeing this delta, what is the name of that delta? Are they the same? Hmm? You should be able to tell that. Is this the same delta or they are different deltas?
They're different on the basis of input.
Yes. What is the name of this one? And what is the definition of this one? Okay. How do you define delta of n? Tell me. Hmm? I'm writing these two conditions, n is equal to 0, n is not equal to 0. What should I write here?
N is equal to 0, it's 1, the integral is 1, and otherwise it's
There's no
0.
integral here. There's no integral. The value is 1 and it is 0. Why? Because this is the Kronecker delta, I told you. This is the discrete time delta, right? Discrete time impulse. Yeah. So it's just 1 at 0 and 0 elsewhere. And why can this delta coexist with this delta? Because this delta takes integers as the input, right? And this delta takes, are these integers?
Real numbers.
Real numbers, right? So the amazing thing is that when you define delta of t, the Dirac delta, you still have to use this t is 0 and t is non-zero, right? But this 0 and this 0, there is a difference. This is the integer 0 and this is the real 0. That's why types are so important. Yeah? 0 alone doesn't tell you whether it's an integer or a real. So you have to view this as a real number, and only then here it is 0 and here it is actually infinity, and the integral has to be 1, right? The integral from minus infinity to plus infinity has to be 1. And I think you can make sense of most of the other entries. A few. Can you give me the entry in this table which was very similar to the first example we did today? Remember the first example where we had this A and B, right? It started at A and it went till B. Which example is similar to that? Very similar, I would say. Hmm?
12th one, exponential
Yeah,
and sum.
the 12th one, right? So that it starts with 0 because it's n minus 0 and it's n minus m. And you can see this thing, right? And as I told you, you have to fix this. What is the problem with this entry? Hmm?
Cases,
This is only acceptable when omega is
not 1,
not
not
0.
0.
Yeah, and when omega is 0, you have to write. You should be able to write that straight away. It was b minus a, right? So what is b here? M, right? And what is a here? 0. So when omega is equal to 0, you should just get m minus 0, right? And one more thing. How mm, can you simplify this thing when omega is 0? What happened to this factor when omega is 0? Hmm? 1, yeah? Exponential 0 is 1, right? And you know this thing just becomes n. So I will leave this to you. Take it as a homework. You should be able to simplify both of these in such a way that the sign there will be replaced with sync, right? You know sync, right? And the sign this will also be replaced with sync. So you will have sync of m, right, by 2 and sync of, and then you will not need these two cases. Sync takes care of both the cases. Leave that, I leave that to you, right? You can do that. And remember that this transform is actually periodic, and here is the proof, right? Although I'm skipping the proof, but you can just follow it up yourself. The reason it is periodic is not because this is periodic, small x doesn't need to be periodic. It is because of this factor which is periodic. And if you try, right, this shift, I told you periodicity is checked by a shift, and you can see that having this kind of shift, which is a multiple of 2 pi, doesn't change the transform, so it must be periodic. Yeah? So it's 2 pi. It's not only periodic, you also know the period. The period is 2 pi. And there are some other properties which you can, then modulation, conjugation, time reversal, upsampling. Upsampling is when you increase the number of samples, right? And downsampling, and when you delete some of the samples and replace them with zeros. Yeah, convolution, multiplication, differencing. So differentiation in continuous time is replaced with. Okay, you need to keep in mind that these slides are for edition 5.0, right? I told you this on GCR as well. And also the lectures. Have you started watching those video lectures which I shared by the same author? Hmm? I mean, you may not have enough time these days, but this is the reliable, authentic resource. So, of course, he has lots and lots of videos. I don't want you to watch each and every video, but you can just search the playlist. The only catch is that it is based on 5.0 and the chapter numbers are somehow not matching. So, yeah, you can deal with that. You know that chapter 7 and chapter 6, the numbering are different, but you can fix that yourself. Yeah. Remember this J thing, right? When X is real, is pure imaginary. Fourier transform of periodic sequences, yes. So when you have a periodic sequence, you will see those deltas. You saw it in the table, right? Because you can only have the generalized transform. So this table actually, this slide explains how to. Um, so if you have a periodic sequence, you just take one period. So you define a new sequence from the periodic one, define it only over one period, and this is now manageable. For this, you can have a classical, right? Discrete time Fourier transform, and to recover the original from this one period, you will need to shift and multiply by delta, shift and multiply by delta, right? And that also appears. So the actual transform will be a sum of these. This is very similar to what we had in continuous time. In continuous time, we also had this issue that the CTFT and DTFT of periodic signals was not straightforward. So we had to come to utilize this Dirac delta. This is similar here. And spectra. You can now recall all these treatments of frequency domain versus time domain. And I mean, if you look at the um, decomposition of a time domain signal as an integral, and you see the transform, the dt of t, you can see dt of t as a weighting factor. You can think of it as a weighting factor attached to a harmonic, because this is discrete time frequency. So this is now the physical meaning of this inverse transform. You want to express a discrete time signal in terms of these periodic harmonics, and this transform tells me how much of that particular harmonic or frequency I need. Yeah, and because this is periodic, so you only need to integrate this over one period. And if you because we also know it's a complex number, so a complex number can be written in polar form. So you write the magnitude as a separate factor, and you see he's also using the word weight for it. And because it's complex, so it's not just the weight, you also have the argument, and the argument will be combined with that argument, and you can easily see that you have a frequency domain analysis. Yeah, so attached to each frequency you have an amplitude and a phase related to it. So the amplitude tells you how much information is at that particular frequency. So you're telling about a signal, and that if I were to construct this signal from complex sinusoids, how much of this particular frequency I need, and the magnitude of the transform tells you that. That's why he's calling it a weight. But that's not enough. You also need the phase. So you will have magnitude spectrum and phase spectrum. This is what we saw in CTFT as well. Yeah, when you want to discuss the spectrum of a signal, you have to plot the magnitude separately and the phase separately. And of course, you have not taken ENA as a course, but this is what they were doing in that course. The Bode plot. They were using Bode plot, and um, you have a magnitude plot and you have a phase plot. So you should also always expect two plots. Yeah, because DTFT is a complex quantity, a complex function, I would say. And the simplicity for real sequences is that many of the things become redundant. You know that the transform is complex conjugate. That it has it has a conjugate symmetry. So if you take the complex conjugate of a signal, they are the same. Yeah? And this only means that you can simply ignore negative frequencies because you can recover all those computation from the positive frequencies. You can draw some analogy. Have you studied the normal distribution in that course which Dr. Shizad Salim is teaching? Gaussian distribution, right? Or not yet?
Um, yes, some part, yes.
So there you will see that bell-shaped curve is symmetric, right? It is actually symmetric around the mean, right? So you only need to know how to integrate one part of it. The other can be recovered just algebraically, right? So we have a similar situation here. Because we know for real sequences the transform has this nice property, so you only need to compute it for positive frequencies, and negative frequencies can just be recovered by this property. You don't need any integration, right? But if the sequence is complex and not real, then negative frequencies are important. You cannot skip them. And you see, we already discussed bandwidth in the case of continuous time, right? So you can now recall those definition. Band limited signal is a signal for which the frequency band is finite, right? So if you look at the Fourier transform of a signal and it is zero everywhere except um, for some interval, right? And because x is periodic, you don't need to look for the entire. If when you were looking at CTFT, if you remember CTFT, right? And we had x of omega, so we had to look at the entire real axis, right? And we had a different definition of bandwidth. But here we only need to look from minus pi to pi. We don't need to look outside. Why? Hmm? We don't even need to plot that because this x is periodic and we know this thing will just get repeated, right? So when we know this is repeated and it will be replicated, so why should we plot it, right? We know it. So in DTFT, you just have to worry about what happens between minus pi and pi. And even there, if it is non-zero only in a specific region and it is zero everywhere else, then this B is what we will call the bandwidth. So bandwidth tells us, you just imagine if B is large, you have high frequency content. If B is small, you have low frequency content. Yeah. And you call it band limited if you had these zeros, right? If you had no zeros, right? And if it was non-zero throughout, and you also know that this gets repeated, so that will not be band limited, right? And the bandwidth of a sequence is the length, right? Over which this is non-zero. So if you think about, if you pay close attention to this graph, um, yeah, the definition of band limited requires this interval. So it has to be an interval. It is not allowed to have this, for example, that okay, it is non-zero here and then it is non-zero here, and that does not qualify as an interval. Yeah. So it has to be an interval, and once you have an interval, then this value is what we call the bandwidth. Not this value, the length. Sorry, the length. So if this is b and this is minus b, the length of this interval is b minus minus b, and that is really 2b. So 2b is the bandwidth. And how do you compute the energy spectra? You can just take the energy of a sequence, right? And this thing, if you think about this integrand only, read it yourself, okay? E is for the energy, x is the signal, but you have this omega as well. So it means that it is not the energy of the signal, it is the energy of the signal contributed by this frequency, right? Why do I say contributed? It is because of this interpretation, right? Yeah, this interpretation that you are actually reconstructing the original signal from these harmonics. So the total energy of this signal will be a sum of these energies, right? An integral, to be honest, because it's continuous. So each frequency will provide some energy, and then you are integrating all those energies. So this is what you see here. Yeah, this is what you see here. This highlighted quantity is the energy contributed by the complex sinusoid at that omega. And because that's not the only frequency, there is a range of frequency from minus pi to 2 pi. So you have to integrate all of them, and then you get the total energy, right? Here is there is something not very cool about this notation. I mean, this the reason you need this x is for the sequence x, okay? And that sequence x is the entire sequence. You can easily write this here as well. There is nothing wrong with writing it there, right? It is still the signal, the energy of the signal x. So what makes this term different from this term is omega, not x. So he's somehow thinking that okay, x is the reason. X is not the reason. Omega is the reason, right? So it doesn't matter whether you write this x or not. I mean, a better way will be to just introduce some new notation, maybe call it tilde, right? And then you are safe. Yeah. Yeah, I think that is enough for today, right? We have time for a few questions. And write P in the chat window, right, before we close the lecture. So we have covered a major transform in discrete time signals, which originally is motivated for aperiodic sequences, but because we know we also need generalized transforms, so that also applies to periodic sequences. So the advantage of generalized transform, whether it's CT or DT, generalized CT FT or generalized DT FT, the advantage of these generalized transforms is that you literally don't need Fourier series. You can skip Fourier series from both CT and DT, and the generalized transform can deal with periodic sequences and periodic signals, right? And the next, I will say, transform will be the Z transform, because just like we introduced stability by the real axis in the S domain, we will need a similar, yeah, flexibility in discrete time. डॉक्टर एरम आपने मार्किंग शुरू कर दी या नहीं अभी तक?
नहीं सर, मैंने आज स्टार्ट करनी है इंशाल्लाह उसको।
अच्छा अच्छा, ठीक है
जी सर।
तो आज के लेक्चर के बाद कितना मिसमैच है कोई?
सर मैंने जो है ना वो प्रॉपर्टीज ऑफ जी ट्रांसफॉर्म स्टार्ट कराना है, मैंने एक्स्ट्रा क्लास लेनी है उनकी फ्राइडे को या सैटरडे को।
अच्छा अच्छा, तो जी ट्रांसफॉर्म की डेफिनेशन और इनवर्स जी ट्रांसफॉर्म वो हो चुका है?
नहीं सर वो नहीं अभी हुआ, अभी आरओसी कराया है जी ट्रांसफॉर्म में।
नहीं तो डेफिनेशन तो पहले होगा, आरओसी बाद में होगा ना। मैं
ये
डेफिनेशन
सर डेफिनेशन और वो हो गया अभी
वो तो कर
जो है वो, उसके बाद प्रॉपर्टीज और फिर इनवर्स जी ट्रांसफॉर्म रह गया।
ठीक है, सही है।
जी सर।
बस एक चीज जो है ना वो अभी करनी है, वो है सैम्पलिंग। सैम्पलिंग का भी कुछ बताना है ना, नाइक्विस्ट सैम्पलिंग और इस तरह ना।
ओके सर।
वो मैं आपको बता दूंगा कि कहाँ से कराना है, ठीक है, क्योंकि आप मुझसे पहले, यकीनन आपका लेक्चर पहले होगा।
ठीक है
We
सर।
need at least one lecture for sampling.
ओके सर।
ठीक हो गया। Thank you guys.